I'm Yisun. I'm a PhD student from Purdue University. Today, I'm going to give you a talk about our recent work, AceDroid, normalizing diverse Android access control checks for inconsistency detection. Before diving into the details of our technique, let's start with an overview of a simplified Android access control model. Android is a layered OS. On the bottom is Linux kernel, which contains all essential hardware drivers, and it mediates all the access to those hardware drivers based on standard discretional access control. And then the framework layer provides many high-level system services, such as activity manager and other system managers. And those system services expose public APIs, which can be invoked by the applications. Upon the invocation of those APIs, the system service is going to do some security checks based on the caller's acquired permission, UID, PID, like other package properties, and even the physical user's security properties. And on the top is application layer. Apps can collaborate and reuse functionalities using intercomponent communications. And the app can protect its privileged functionality by configuring several security properties. However, several research works have questioned the effectiveness of Android access control model. With the lack of an oracle, actually, it's very difficult to determine if a resource is correctly protected. And there's one approximate solution to this, to compare the access control enforcements across multiple instances of the same resource and report inconsistencies as potential vulnerabilities. There are several prominent works on this. At the Linux kernel layer, Addicted compares the protection level of hardware drivers on a vendor's version to its corresponding LSP version and report inconsistencies. And DroidDiff compares the security configurations, such as permission and app configurations across different Android images. And on the framework layer, Kratos, which is most related to our work, it compares the set of security checks on multiple APIs leading to the same resource and report inconsistencies. As I will show later, many challenges can now be addressed by the existing work Kratos. Okay, before diving into talking about the challenges, let's first look at an example of exploitable inconsistency. As we have discovered in Sony Xperia XA device, there are two APIs that can lead to a system shutdown by invoking the underlying sink. One is called device managed.reboot, and another one is power managed.reboot. The power managed.reboot first is going to check if the caller has a permission.reboot, which is the system level permission. And the device managed reboot implements a much diverse but weaker access control. It first going to check if the caller is system by checking the UID. And or it checks if it has a permission called permission.enterprise API, which is a custom API introduced by Sony. It might look okay if that permission is as privileged as permission.reboot. But after further investigation, we find this permission is actually of normal level, which means it can be acquired by any third-party apps without user consent. And this API follows with a check of the user ID and determine if the user is the owner of the device. So this inconsistency reveals a vulnerability in this device that a third-party app which cannot call power managed.reboot can successfully call device managed.reboot and trigger a system shutdown with a normal privilege. So from this example, we can see framework developers actually do not have a gold standard to implement the appropriate access control. And therefore, there are diverse ways can be used to achieve the same protection as the framework layer. If not taking that into consideration, this diversity can lead to a significant number of false alarms when doing the inconsistency analysis. Let's consider this following example as the false alarm example. We found there are two APIs in Samsung device, both can allow to install an application by invoking the underlying sync. The install package for MDM implements a very concise access control. It'll first check if the caller is system, and then it checks if the user is restricted from installing apps. And the install package as user, it first checks if it has a system permission install package, and then it checks if the system, or it checks if it has the system permission interact across users. And then it also checks if it has the user restriction. So it might look that these two APIs are syntactically different, but actually from the perspective of a third-party app, they are semantically equivalent. Because for a third-party app, it cannot obtain the UID 1000, and it cannot acquire any of the system permissions. Therefore, this inconsistency is actually not exploitable. Let's see how the existing work Kratos is going to handle this situation. Kratos will union all security checks from entry point to the sink, regardless of the program structure. And it only considers a number of explicit checks, like a permission, UID checks. So for this case, for install package for as user, Kratos will present a security check as following. Permission equal to install package, UID equal to 1000, and permission equal to interact across users. And for the other API, it will present the security check as UID equal to 1000. Please note that Kratos doesn't consider the check for the user restrictions. And based on these extracted features, Kratos will identify these two APIs are inconsistent. But we'll argue that this is not the appropriate way to perform inconsistency analysis, as they are actually equivalent. They are equivalent from the perspective of a third-party app. Okay, so we propose to conduct access control normalization to detect exploitable inconsistencies. Our technique normalizes various security checks to canonical values following the program semantics, and handles different program structures such as if-else and loops. And this allows more precise and concise comparison across different implementations. So let's see. Under our technique, both APIs will have the following concise canonical value, which means that both two APIs require the app to have a system-level privilege, and the user shouldn't have the restriction to disallow install apps. So based on this canonical value, we can see actually these two APIs implies consistent access control enforcement. For detail, we model each access control checks as a pair of app and user aspects. App aspect aims to check if the app that tries to access the resource has the needed credentials, and user aspect determines if the user of the app that tries to access the resource has a certain role. And further, we model each aspect as a vector of multiple dimensions. The first dimension of app aspect is privileged. Privilege checks are to determine if the calling app owns certain privileges. For example, to reboot a phone, the system services require the caller to have a permission, android.permission.reboot. To normalize this permission, we normalize it based on its Android protection level rather than its name. So we have system as the highest protection level, followed by dangerous, and followed by normal. Other privilege checks can be enforced based on UID, PID, and package properties such as signatures. We further normalize our normalization handles various program structures. For example, if multiple permissions are enforced, here there are two permissions, and we intuitively take the strongest one as our normalization value. So here, for this example, we will have a system as our normalized value. In contrast, if either permission is enforced based on a try-catch or a if-else structure, we intuitively take the weakest one as the normalized value. So for this example, one system, one is normal, we have the normalized value normal. Then the second dimension of app aspect is resource owner. Resource owner checks decide if the calling app is the owner of the resource and grant access to the resource accordingly. As such, the caller that does not need to hold any privileges if it is the owner of the resource. And due to time limitation, I will skip this example. And the third dimension is status. Status checks if the calling app is the foreground app, as some accesses are denied for background apps. The second aspect is user aspect, which has been integrated into Android access control model with the introduction of multi-user features. Similar to app aspect, user aspect includes privilege check, resource owner check, and status check, and the restriction check. Due to the time limitation, I will not talk in detail. If you are interested, you can look at our paper. Okay, now to illustrate how we model security checks for a given API, let's look at this example. This API will first check if it has the permission manage network policy. If so, it checks if it has a permission read privileged phone state. If not, it checks if it has a permission read phone state. And it will return the network policy accordingly. To model this API, we're going to first map the last checked permissions to its protection level. For read phone state, we'll map it to normal. For the other one, will be mapped to system. Because this is an if-else structure, it will be further normalized to normal. And then we map managed network policy to system. And because this is an additional check, the normalized value is going to be the maximum of the two, which is the system level. So similarly, we can model and normalize other checks corresponding to other app and user dimensions. We conduct two different types of inconsistency detection. First, in-image analysis. It compares access control to a same resource to discover inconsistencies. And cross-image analysis, which identifies inconsistencies along similar APIs across two different Android images. To conduct the analyze for each input room, we first extract the framework class files. And then we collect the system services and identifies the entry points for, that are publicly accessible. And then for each entry point, we build a call graph. And then we model and normalize the security checks appearing in that call graph. To conduct in-image analysis, we will first do a conversion analysis for all the entry points and to identify if two different entry points leading to the same sink. And then we compare the modeled and normalized security checks of the two different API and to see if there are any inconsistencies. For cross-image analysis, we compare access control enforcement of the access control enforcement of the same public API across different images and report inconsistencies. Here's our evaluation. Here we show the in-image result. Each column and the row represents one unique image. For each cell, it shows the actual vulnerabilities over reported inconsistencies. As shown in the table, not all reported inconsistencies are vulnerable. And on average, we achieve about 69% of true positive. And please note that on average, we achieve about 63% increase over Kratos true positives. And we can see from this table, the customized rooms exhibit a higher number of inconsistencies compared to the original version like a Nexus. And here in this table, we show the evaluation result of cross-image analysis. As we can see from the table, inconsistencies are prevalent across different vendors and even within the same vendors. For example, when comparing S6H with Samsung, when comparing Samsung S7H with Nexus 601, we find 21 vulnerabilities. When comparing Samsung Tab S with another Samsung version, we also find 12 vulnerabilities. Last, we want to show that the previous results are after normalization. To demonstrate the usefulness of our normalization process, we also report the number before doing normalization. You can see, for example, when comparing S7H with Nexus 502, before normalization, the reported inconsistency reached a tremendous number of 562. But actually, there are only 39 actual vulnerabilities, which means there are over 500 false alarms. And by doing the normalization, on average, we can reduce the false alarm from over 200 to 13. Okay, last, let's see some findings which are confirmed attacks. We picked the instance for which we have the actual device and confirmed 27 actual vulnerabilities that can be used to conduct attacks. And we poll those attacks to the corresponding vendors. Over 20 of them are acknowledged and reproduced by them. 2 are ranked as critical by LG. The first one, it allows eavesdropping on input events such as screen taps, and the other one allows intercepting and injecting input events such as screen touches. So we can see actually we found some very dangerous vulnerabilities. Okay, that concludes my today's talk. And thank you for your attention. I'm here to take any questions. Thank you.
So I was thinking, you mentioned you found 2 critical vulnerabilities in the LG devices. Can you elaborate on how the permission checks were actually exploited in order to conduct those 2 attacks?
Okay, so for the let's see, for the LG image, we actually find that during our cross-image analysis, we find that in LG G4, it exposed a system-level API, which is hidden in other images, which means it has a very high-level privilege, but it is not correctly protected in LG. So we use that API. We create a service that can call that API to get the coordinates of each tab. And for the intercepting one, it's similar. The developer of the LG framework maybe mistakenly exposed the API that it should not be exposed. We found that and registered to the Windows service, and we can use that. We can intercept any input event we want. Does that answer your question? Okay. Thank you.
All right. If there's no other questions, we'll move right along. Let's thank our speaker again.
Thank you.